So the last thing that we need to do today is to talk a little bit more seriously about what it actually is to be a solution to a differential equation. So far we've found lots of solutions. We've talked a little bit about being a general solution or a specific solution, but there are some subtleties here which actually turn out to be quite important, even in the real world, when you're finding solutions to differential equations that you've put together to solve things like intracochlear drug delivery or whatever. So although this might seem a little bit technical, it is important, because particularly when we use computers to find solutions, often computers don't know the details of the mathematics behind things. They're just going to do whatever they can do, and we need to be able to look at what they present us as the solution and go, is that right? Can that be true? Is that the only possible answer? All right, so here we go. So the first thing that we need to do is define exactly what it means to be the solution to a differential equation, an ordinary differential equation. So let's put together a definition that is going to kind of make sense, and we'll take it step by step. All right, so a solution to an ODE. What are we going to do? First, we're going to take a function of two variables, our time variable and our u, which is actually the function that we're trying to find. And we're going to let it be defined in a rectangle on the TU plane. Okay, nothing crazy here. All we're imagining is that if we're going to plot our solution, we would plot it t versus u, and we're thinking of that as the TU plane. So this is our TU plane. And we are thinking about some rectangle in there. So just some r, and the way that you would think about that r is that it's x, and it has an x start and finish, which is a and b, and a y finish, c and d. Okay, so we've defined some rectangle r within our TU plane. And what we'll say is that a function u of t is a solution to the differential equation given by du by dt equals this f that we've got over here, if two conditions are met. This function that we found is defined on our rectangle. So it's defined for a is less than t is less than b. So our function, our solution, has to be defined for everything in that range there, for all t values there. And it lies within the y range of our rectangle R. So basically what we're saying is something like that is great, something like that, which is not defined at all a and b, and also moves out of our R, is not okay. So that's not okay, but our green would be okay. And then we have another little criterion that we need to have, which says that our solution function must be differentiable and hence continuous, because differentiability implies continuity, but not necessarily the other way. So it needs to be differentiable for all t in our range a to b. And this is the important thing, the derivative of our solution function must be equal to our original thing, because what we wanted to do was find a solution to that equation over there. Okay, so it doesn't sound like we've said very much, but it is a way of kind of nailing down what it means to actually be a solution and kind of getting rid of cases which might create problems. So we've seen, and if you go back and check all the solutions that we've found and think about what our bounding box, our big R, would be, everything's been fine. But let's have a look at an example which has a little bit of subtlety, even though it looks like an innocent little differential equation. Okay, so we're looking at du by dt is equal to u squared, and we're going to look for the solution which has the initial condition when t is equal to 0, u is equal to 1. Okay, well, let's see what we can do. So let's start by solving this differential equation. So you have a look at it and you go, what is it? Well, it's not linear, so we're not going to be using the first technique, but it is actually separable because there is a notional little 1 over here. So we can take our function of u, which is u squared, over to the left. So the first thing to think about in terms of this definition over here is that this u squared here is our f of tu. Okay. The next thing to think about in our definition is what would our r be? So in particular, what are the t values for which we want to find a solution? And initially you might look at this and say, well, I mean, that derivative, that du by dt is defined for all t, so maybe we want to find a solution for all t. So maybe a is equal to minus infinity, b is equal to infinity, because it's good to know, I mean, we kind of have to know where is our solution valid. Maybe, I don't know, we can check on that. Okay, so far we've just done a little bit of thinking around this. Let's solve this. So we use separation of variables. So I'm going to have 1 over u squared du by dt is equal to 1. And the important thing here, if u is not equal to 0. Because if it's equal to 0, then we just divide it by 0 and the universe exploded, and that's bad. Okay, so separation of variables says once you've done the separation, you integrate both sides with respect to dt. And then the magic happens, and essentially what you end up doing is 1 over u squared du is equal to integral of 1 dt. So these are nice and straightforward. So we've got minus u to the minus 1 is equal to t plus c, where I've just folded in the constant from this side into the constant on the other side. Okay, and now we want to find our value of c because we've got an initial condition. So we let u be 1 when t is equal to 0. So that gives us minus 1 is equal to c. So let's plug that in. Minus u minus 1 is equal to t minus 1. And if you do some swapping around and some algebra so that we can write this as in the way that we want, we get that u of t is equal to 1 over 1 minus t. Okay, so that's our specific solution. And this is the bit that we're going to kind of start being more careful about from now on. Up till now, we've just said that's a solution and we've moved on with our lives. But you will notice that what we've defined here as a solution, it's not enough to just have an equation. You also need to give the domain for that equation. And the domain actually has to be a continuous strip. So part of what this is saying here is that the domain of the solution is a continuous chunk of the independent variable, in this case t's domain. So what happens if we try and sketch this function? Well, I'm going to trundle over into Geogebra where I plotted it earlier. So I've just plotted it using y and x, but y is my u and x is my t. And if you plot it, you'll see that you get this bunny over here. Let's just take a picture. So you might be wondering, why am I going to all the trouble of showing you the plotting in Geogebra? Why don't I just put the image in here? I'm showing you because I hope that you will start using Geogebra or an equivalent plotting tool to do this yourself. because it's a key feature of being able to do any kind of applied maths like this. Okay, so here we have plotted our u of t, which is equal to 1 over 1 minus t. And you'll notice the salient thing here is that this function is not defined. So this is t, and that's u, and we're not defined at t is equal to 1. And this is a bit of a problem, because if we say that our solution is valid from minus infinity to infinity, then we have a point where our solution is not actually defined. And according to our definition of what it means to be a solution, you have to be defined everywhere within the range, within your kind of domain as a solution. And that has to be a continuous, strip. So the best that we can do here is say that our u of t is a solution, for example, minus infinity to 1, because that would give us everything up to here. So u of t or perhaps it would be more appropriate, depending on whatever this differential equation was modeling, you could say, okay, from 1 to infinity, but it's going to have to be one or the other. It can't be both of these two continuous regions, because there's a gap here. So you pick whichever one, and that is the domain of your solution. Okay, so I'm leaving, this is region 1 and this is region 2. So it couldn't be a solution on both. You either say it's the solution on one or it's a solution on the other, and there's no bigger domain that it could be a solution on. So from now on, when we solve DEs, except when we forget, we're going to not only give the explicit solution for the DE, we're going to say what its domain of validity is. So here we would say it's our specific solution, and usually we give the biggest possible range of numbers that it is a solution on. So here we would say minus infinity up to 1, because that's the biggest. And if you want to get into an argument about the size of sets, we can have that after class, because someone is probably going to point out to me that minus infinity to 1 is about the same size as 1 to infinity. But we won't go into that. Just looking at this and kind of thinking about it, we're going to say, okay, minus infinity to 1 is bigger. Welcome to mathematicians not being as rigorous as you might think they would be. Phew. Okay, so now we've actually just, all that we've done is defined what it means to be a solution. So when you find something, you know that you found a solution. And the key thing coming up here is it's not enough to just have an equation. You need to say over what continuous range is that equation true. Okay, so it's a little different from finding the domain to a function, because the domain for a function might exclude points, or it might only be defined in chunks. Here we have to have just one continuous chunk to be a solution. So when we talk about the maximum possible domain, it's the largest interval into which the solution can be extended. And that's called the maximum domain. You can read through these other things. There can be all kinds of problems that mean that you don't have a continuous function, so maybe it blows up at some time t, so that we saw over here. Our function blows up to infinity as you approach 1 from the left, and it goes down to minus infinity if you go from the right. but you can also have other kinds of discontinuities. So, I mean, one of the things that I feel is that this course is one of the most useful places to have studied calculus. I think often in calculus, you wonder why we care about things like limits and asymptotes and stuff. And honestly, you really need it for differential equations, figuring out asymptotic behavior, things like that. Okay, so just a kind of a word of warning, if you go further on in DEs, probably further than we will in this course, you can encounter some solutions that are not differentiable or continuous, in which case the definition that we just gave falls apart. But for pretty much everything that we're doing for this course, it'll do. Okay, so now we've defined what it means to be a solution. But the question you might want to ask is, if I hand you a differential equation, how do you know that you can find a solution? And if you can find a solution, how do you know if that solution is unique or if there might be many solutions? And we want to kind of have a mathematical definition, just like we had a definition of what it means to be a solution. We'd like to have a definition or a theorem that we could use that will help us so that we can look at an ODE and go, okay, well, at least I know I'm not wasting my time trying to find a solution here. I know that one exists and I know that it's unique. Or alternatively, there's going to be a problem here. Okay, so this is an important question. We don't want to waste our time. So let's have a look at an example ODE. So we've got du by dt is equal to t cosine of, and then inside the cosine we've got, oh wait, no we don't, cosine t times cosine of u of t minus sine of t. So not linear, okay, and it's not separable. So at the moment we don't really have techniques for solving this. So the most tempting thing might be to just quickly draw a direction field. And conveniently we have one over here. And it looks pretty reasonable. And if you look at the initial condition at t equals 2, u is equal to 3. So let's have a look here. At t equals 2, u is equal to 3. So that's somewhere here. It looks like you should be able to, at any rate, computationally find a solution, because you could certainly follow something down here. And it looks like it probably came from there. So it looks like there should be, that got a bit wobbly, but anyway, it looks like there should be a solution. And in fact, on the panel on the right here, so they've zoomed in a little bit. So we're starting at the point 2, 3 here. It looks like you should be able to find a solution. And the reason one would think that there's a solution is because it looks like all the derivatives, all our little vectors, are kind of behaving reasonably. There's nothing crazy happening. So if we think about what criteria we might require of our differential equation in order to have a solution, we're going to have to think about the derivatives and continuity. And in fact, that's exactly what happens. So there are several different existence and uniqueness theorems. This is just one of the most common ones that's used particularly for ODEs. And it builds on our idea of what it means to be a solution. So once again, we've got a rectangle, which we had before. So we are always thinking in the TU plane. And we have a rectangle, just like we did before. And its width is b minus a, and its height is d minus c. So this is our rectangle R. And we're going to suppose, and again we have our function tu. So remember that function was the thing that we were going to make our du by dt equal to. Okay, so we're going to assume that our function is continuous at each point in R. So this is the first point. It's continuous at each point in our R. And the second point is that the partial derivative of our function with respect to u, not with respect to t, is continuous at each point in R. Okay, so that is a bit of a strange one. And it's actually not a super strict requirement, but it is important. Okay, so we've got our function, so we're going to have our ODE here. So this is our du by dt is equal to f of t and u. And our requirement says that this f has to be continuous, and we need to have that df by du is also continuous. So notice that what we're saying when we say that our f of t and u has to be continuous is that we're saying that du by dt has to be continuous because du by dt is equal to f. So we're really saying that du by dt, so our solution has to be continuous. Sorry, the derivative of our solution has to be continuous. Okay, so if those criteria are met, then for any point t naught, t equal to t naught and u equal to u naught, so if I take any point in here, so let this be the point t naught, u naught, the ODE that we're interested in, which is this bunny over here, has a solution with u of t naught equal to t naught, so it has a solution that goes through this point here on some interval that lies kind of around. So let's just put this here, that's t naught. We can find a solution on this region here. So that's t naught minus delta 1, and that's t naught plus delta 2. So this sounds very complicated, but really all we're saying is that if you have a function t of u, a function f, which is a function of t and u, and it's continuous, and its first derivative and its partial derivative with respect to u is continuous, then if we find a solution, if we're trying to find a solution to the if we're trying to find a solution to the ODE du by dt equals f of t and u, and our f meets these small criteria, then we can, at any point, for some region around that point. If you think about what this means, basically it says, okay, well, I can start looking at this point, I can find my solution around a little bit. I can look at this point and I'm guaranteed to find a solution over there, and then I can move a bit and I'm guaranteed to find a solution. There is one word that we left out, and that is that it's a unique solution. So that takes it even further, and it says that if I start here, I will find a solution that looks like this. And if I move over here, I've found a solution around a little bit, and then I move a little further, and I'm still within the range where I found a solution. If I look at that point, I will find the same solution, and I can extend my range a little bit further. So it basically allows you to build up a unique solution within your R, given an initial starting point. So this is quite powerful, because the criteria that our f is continuous and its partial with respect to u is continuous is not particularly onerous. So this is a way of guaranteeing for yourself, if you look at an ODE, that you can find a solution on a particular R. So let's have a look at an example here. So we have the one that we've just seen there. Okay, so here our f of t and u is t cos of u minus sine of t. And that is continuous everywhere, so that's delightful. So this is continuous for all u and t, so it's continuous here. So in fact, our r here, so far, our r could be the whole Euclidean plane. T is minus infinity to infinity, and u is minus infinity to infinity. Now let's just have a look at df by du. df by du is our partial derivative of f with respect to u. So that's going to give us minus t sine of u, and that's all. And if you have a look at that, that's also continuous. For all u and t. So basically what this theorem says is there is definitely a solution, a unique solution to this ordinary differential equation for the whole Euclidean plane. It doesn't guarantee that you can find it, it just says that there is one. So our theorem here okay. It might be that you need to find it numerically. As I said, you might not be able to find it analytically, but there is a solution. Okay. What are the implications of this theorem that sounded so technical for sketching solutions? Well, our existence and uniqueness theorem actually tells us some quite important things for when we're sketching solutions. For example, could we possibly have a case like this? Well, in fact, our theorem says you can't have a situation where two solution curves cross because it says it's a unique solution. But at this point over here, right where they cross, the implication is that we have two different solutions. So nope, not going on there. And in fact, you can't even have a situation where two curves kind of meet each other and then so only meet at a single point, because that's still going to give you an issue as far as the uniqueness goes. So you know if you're drawing solution curves, they never intersect and they are never tangent to each other. So what does it mean for ODEs if they don't meet the criteria of theorem 2.4.1? Well, the theorem is only an existence and uniqueness theorem. So it says if you meet these criteria, then we can guarantee that you have a unique solution. But if you don't meet the criteria, that doesn't mean you don't have a solution. So it's really just a case of if you don't meet the criteria, you need to find some other way of analyzing your ODE. It could be that it has a unique solution. It could be that it has no solution, and it could be that it has infinitely many solutions. So let's have a look and see. So here's an ODE that we might want to solve. It looks pretty innocent and straightforward. So we need to think about, firstly, the continuity of this bit, because remember, we're saying that our function on the right-hand side of our ODE has to be continuous, and then we also need that the partial with respect to u is continuous in our region. So this is our f of t and u. So f t u is equal to, and if we think about where is that, so we're thinking in our two-dimensional space, well, that's actually continuous everywhere. It's continuous for all u, continuous for all t, so that's great. But the problem comes when we have a look at the partial with respect to u. If we do that, then we get 2u to the minus a third. And that is not continuous because it's not defined at u is equal to 0. Oops, so not defined is definitely not continuous. So this just means that we can't use theorem 2.4.1 to guarantee that we can find a unique solution. But if you do some work, so you can see that this is separable, you can do some work and you can find that the solution is actually u of t is equal to t cubed. And if we think about what the validity of that solution would be, that's going to be defined. So we're now thinking about our definition of the solution, not about the theorem. So if we look back at our definition of the solution, what does it mean to be a solution? We say U of t is a solution if, well, it solves the dE. It's defined on the t range that we specify, that it doesn't go outside the bounds of the R range, and that it's differentiable such that its derivative is equal to our f. Well, let's have a quick check. Oops. So this is a solution. I claim it's a solution on R2. The only things that we really need to check is it continuous. It's continuous everywhere. It's defined on all t from minus infinity to infinity, and it goes from minus infinity to u. And if we need to make sure that it satisfies the original equation. Well, let's have a look. So we want du by dt is equal to 3t squared. And you might go, that doesn't look like what I thought. But remember, our original dE was that du by dt is equal to 3u to the 2/3. And if u is equal to t cubed, then u to the 2/3 is t cubed to the 2/3, which is equal to t squared. So in fact, our du by dt is equal to 3u to the 2/3. So it satisfies our original differential equation. It's continuous everywhere. It's differentiable everywhere. So this is a solution on R2. We just had to kind of hope that we would find it and then check that it is a valid solution, because we couldn't use theorem 2.4.1 to guarantee it. Phew. Okay, so that's been quite a lot for today. We will consolidate most of the kind of the practicing written stuff in the first tutorial, and then we'll use MATLAB in the second tutorial to kind of look at how one works in practice with DEs, because there's very little time spent actually just handwriting solutions. All right, so I will look forward to seeing you all on Wednesday.